All right, so let's take a look at a program that ties all that together and also does some reading and some writing over the connection. So first, let's take a look at the client side. This is again in 16code.tar.gz. This is the Echo client. Echo is a particular service, although we're going to not run on the usual port number for reasons I'll explain in a moment. Echo is a service where the client connects, it sends something, and the server sends it back. So pretty simple. In this case, it's going to work line by line. So every time we print a line, the server will read that and spit it back at us. So we're going to do the client side of the connection. Now remember, on the client side, we need to call socket and we need to call connect. But rather than doing that directly, we're going to use this open client FD function. So this is in csapp.c, which is the same as we've had for several of the example code files, but it in particular has some networking functions that'll be useful to us. Open Client FD does that entire sequence of calls. So get adder info. Open Client FD is taking a string for the host and a string for the port, just the things that were passed in on the command line. And it will call get adder info to get a struct sock adder that it can use. It will call socket to create the socket. Then it will call connect to connect to that particular struct sock adder. So if we look at csapp.c and look for open client FD, well, it's actually a wrapper for lowercase open client FD that just checks for an error and reports it here. So the real open client FD is right here. So we have the host name and port. We set up a struct adder info, hence, same as we did in the host info program. We say that we want TCP, so we want a stream rather than sock dgram for datagram. The server, or the service rather, the port will be specified numerically. So remember, it is still a string, so it'll be a string of digits, and that will be converted into a number. And AI adder config, what's that about? So if the flags includes adder config, then IP addresses are returned only if the local system has at least one IPv4 address, and IPv6 only if the local system has at least one IPv6 address. Okay, so that makes sense. That is saying that if we have a IPv4 address, which we do, then it's okay to get an IPv4 sock adder info. And if my computer has an IPv6 address, which I happen to have, then I can get a IPv6 address. That way we don't have to worry about checking which is actually supported. We don't have to worry about looking up something, getting an IPv6 address, but only having an IPv4 network. We'll get the kind of address that we can handle. So it calls get adder info, passing in that stuff. Remember, the result of get adder info is really this list pointer. We have to pass in a pointer to the pointer. Then we can iterate over that. It's a linked list. We'll try to create a socket. If that failed, that's not a fatal error. Remember, we have this linked list of addresses we can connect to. If we try to connect to one and it doesn't work, or we try to set up that kind of socket and we're not able to, maybe we're not able to make an IPv6 socket on this computer, then we will get an error, but rather than aborting the program, we'll just continue the loop, go to the next iteration, and we'll take the next thing in that linked list. Once we've got the socket created, then we'll try to connect. If that connection succeeds, so if it doesn't return -1, then we're done. We will break out of the loop. We don't need to look at subsequent adder info entries. We found one that works. And if it didn't work, so if it did return -1, then we will close it, repeat the loop, and try again. If we go through this entire loop, then either we succeeded, and this called break, or did a break, or we went all the way through the list and we didn't find anything. We'll free the entire list, and well, if we went through the entire list and didn't find anything, that means we got out of the loop because P was a null pointer. So if P is a null pointer, if it's false, we'll return -1, indicating failure. Otherwise, we'll return that file descriptor. So let's go back to the Echo client. So OpenClient-FD did all of that connection process. Now we're going to use RIO read init B. So this is something specific to the CSAPP library. RIO is a collection of functions to do raw IO. Raw as in it works at the file descriptor level rather than buffered file streams like stdio or cout. But it's a little bit higher level than just using read and write. In particular, read and write can, particularly when we're working with networks, give us a short read. We read less than we asked for, or a short write. We tried to do a write, but not everything got written. So the RIO library handles all the resending and so on that's necessary, and allocating buffers and so on. So we will initialize this RIO with RIO read init B, passing in the client file descriptor. So we're initializing it for read. We can call fgetS on standard in. So this is reading what we type into the keyboard. As long as that didn't give us null, as long as we were able to read, we will write to the client the buffer, the length of the buffer. RIO write in will handle calling write the system call as many times as is necessary, and then we'll read a line back using this RIO. This is going to read a line, so if it does one read and only gets a few bytes but not an entire line, including a new line, it will keep going. It also handles making sure we don't have buffer overflow. It takes the length of the buffer and won't go past that. And then we'll write what we got back from the server, which should be the same thing that we typed, to standard out. So that's the client. If we just run the client, it's not going to do much. Let's try this. Well, if we happen to know the HTTP protocol. Oh well. Let's try that again. Get. So well, we can at least talk with some server, but really this is designed to talk with the echo server. So the echo server is the other end of this. It's going to create a listening socket, then accept connections on that listening socket. When it gets a connection, it will read whatever the client sends, write it back out to the client, and keep doing that until the client closes the connection. While it's handling one client, this version of the echo server isn't going to be able to handle other incoming connections. They will just have to wait until the first client is finished and the first client disconnects. We'll see in a later chapter how we can do a little bit better than that. So we use OpenListenFD. This is also in the CSAPP library, just like OpenClientFD. We pass it in argv1, which is the port number, and it will do socket or get adder info, socket, bind, and listen, and return the listening file descriptor. Again, we can't read from that or write to that, but we can call listen on it. So in a loop, we will. So what is this struct socket adder storage? This is a structure that is defined to be as big as any possible struct sock adder could be. Remember that plain struct sock adder isn't big enough for IPv6 addresses. It is big enough for IPv4. But struct adder, sock adder storage will make sure we have enough size. So we'll use that as what's called client len. We'll call accept, pass in the listening file descriptor, the client address, which is that struct sock adder storage, or its address rather, but cast to a struct sock adder. We'll pass the client len. Notice we're passing a pointer to the length because accept will figure out what the length actually was and update the length that this pointer points to accordingly. So we've got the connection that gives us a connected file descriptor. It gives us the address of the client as a struct sock adder. We'll call getNameInfo with that struct sock adder, the client length. We'll also give it the buffer that we want to write the host name and the port of the client side to, and the sizes of those buffers. And then we'll print a message, and we'll call this function echo on the connected file descriptor. Once echo returns, we'll close the connected file descriptor, and we're done. So let's see, echo. Echo uses that RIO library again. It initializes the RIO with the file descriptor that it was passed in. It will use that RIO object in RIO read line B to read a line, storing it in this buffer. And when it's gotten a line, it will print that the server received how many bytes and write the result back over that connected file descriptor. So echo server, notice this is echo server I. This is the iterative version. We'll see versions that handle multiple clients at the same time in a future chapter of the book. I give it a port number. Now you might think, okay, well, let's give a port number like 80. I don't have a regular web server, or I don't have a web server running on port 80 of this machine. But I get permission denied. Well, it turns out that port numbers under 1024 are, by convention, and this is enforced on Linux, reserved for the super user, reserved for root. The idea being, I don't want just anyone who has an account on my computer to be able to be the web server for my computer. So many of the known services in Etsy services, things like SSH and HTTP and FTP and so on, are on port numbers less than 1024. So only the super user can listen on those ports. But I can pick something over 1024. Any user can bind on those. It's not that a regular user can't run a web server even, just not on port 80. So let me do 1999. I don't think I have anything running on this port. Well, okay, it's listening for connections. What am I going to do now? Let me put the server in the background. And now let me run the Echo client. Tell it to connect to localhost, the local machine, on port 1999. So the server is reporting that it got a connection from localhost. Well, the client and the server are on the same machine, so they have the same address. This is the port number of the client. Notice it's a pretty big number, indicating it's likely to be an ephemeral port number. And now on the client, I can type in hi, press enter. The server reports that it received 3 bytes, writes that back to the client, and then the client spits out hi. If I want to disconnect on the client, I'll press Control D. That will cause it to get a end of file on standard in. And in the Echo client, remember, it was running in a loop when it gets a end of file, when fgetS returns null, then it will exit that loop and call close. When the server sees that connection is closed, it closes its end of the connection as well. The server is still running, so I can connect to the server again. This time, if I connect to my host name, then I'll see on the server the host name of my client is nmore0. Notice it wasn't localhost. Localhost is actually the IP address 127.0.0.1, which on any computer refers to that computer itself. This is the external, well, actually only on UK's network, but external to my machine, IP address for my virtual machine. So I'm connecting to that here, but I could also connect to this from anywhere on UK's network, or from a machine that's connected to UK's network through the VPN. And so I will Control C the client, which just terminates it. Fortunately, when the process is terminated, all of its file descriptors are closed if they only belong to that process and aren't shared with another one. So that connection did get closed and the server is back to listening. So let me bring the server back to the foreground, stop it with Control C. So I also wanted to point out, but I'm not going to go into detail about, in the subdirectory tiny, we have an implementation of a web server, a very simple web server. It doesn't support encryption, of course, and it only supports a very, very, very limited subset of HTTP, but it's enough that you could run it on a port that's not 80, or if you're root, even on port 80, and connect to it. If you run it on your virtual machine, of course, you can only connect to it from campus or the VPN, but if you were to put this on something you had in the Amazon or Google or Microsoft or Dell cloud, then you would be able to connect to it from anywhere on the internet. So we can see it has several functions. It does the OpenListen FD, except the same as we did in the Echo server, the same kind of get name info. But instead of calling that echo function, it calls another function called doit, which is more complicated because it needs to parse out the request, check whether the file name can be accessed, report back a 404 error, not found error, and so on. So you can read more about HTTP and more about this program in the rest of the slides for lecture 16. You can read over the program to see how it works. Unfortunately, it's not very useful for the real world because these days most web servers provide encryption, and users want encryption when they're connecting to their web servers, particularly if it's something that you're going to log into. If you don't use encryption and someone sends their username and password over that unencrypted connection, anyone who's on their network or on your network or one of the networks in between can overhear that, and that could be a problem. So typically for anything involving usernames or passwords or access to any kind of limited or sensitive resource, and really for just about anything, web servers these days typically use HTTPS. However, that encryption process is much, much more complicated. Besides just doing encryption, we also have to negotiate over the connection to decide which cryptography algorithm to use. We have to set up the connection. We have to set up a server key and a client key. We have to validate the key of the other side and so on. So it really is a fairly complicated process. But with this program, you can at least see how things were in the good old days of Wild West, no encryption web servers, rare though they might be today. But anyway, that's all for today. So next chapter of the textbook will be about concurrency. We'll see more about that later. If you haven't yet started on Program 4, I highly recommend it. I may send out a video in a few days about Program 4, but definitely don't wait for that to get started. It's due this upcoming Friday, so you don't have a lot of time. As usual, it can be submitted late with a late penalty, but ideally you'll get that in. Remember that it's based on Lab 3. A big part of what it needs to do will be already there in Lab 3. That will probably be somewhere between a third and a half of your code, depending on how precisely you write some of the things you need in main. But anyway, thanks a lot, and I'll see you in a few days.